Thank you, Andrea. So I will do now a couple of exercise hands-on, and then Iurii will take over for another exercise later on. So let me share the screen. Can you see it still? Andrea, is everything looking?
Yes,
okay.
we do.
Okay. So as exercise 3, we now approach the calculation of chromium oxide. So chromium oxide still has the same rock salt kind of unit cell that we saw before, both for cobalt oxide and iron oxide, which is given in this picture. Basically, we have a rock salt crystal and the transition metal ions here in red. I have magnetization, so I have a finite magnetization because of Hund's rule, and in particular, these transition metal monoxide are typically characterized by an antiferromagnetic ground state that is based on the alternation of ferromagnetic plane, 111 plane of transition metals that alternate with opposite magnetization with respect to the neighbors, as shown in this picture. So basically, although it's two FCC interpenetrating FCC lattices, you have to pick a unit cell that's twice as large as the FCC one, the regular FCC one, just because you have to allow for antiferromagnetic type of structure. So you need at least one transition metal will spin up and the other one will spin down to capture this ground state. So the smallest one that we can base these calculations on is shown in this figure. Okay, so it's given by these three vectors pointing from the origin to these three transition metals. That's a rhombohedral kind of structure. So everything looks the same as for the other transition metal monoxide we have seen so far, but of course each of them is different. So chromium 2+ in particular has 4 d electrons. And because of Hund's rule, the first Hund's rule, all of them are in the same spin channel. So they tend to align the spin, and that would be the majority spin channel, as we will see in a second, also from the output of our calculations. And of course, as I mentioned before, one of the chromium will have spin up, the other one will have spin down, and that's how we render this antiferromagnetic ground state. Okay, if we do the band structure of this system using the standard approximations for the exchange correlation function, we get something like this. We get a nice separation between P-like state low-lying here from the oxygen, while the D states from chromium are around the Fermi level here. But since they are partially filled, this manifold of these states crosses the Fermi level. Okay, so that's how our band structure calculation renders the partial filling of these states of the transition metal. If we do a blind DFT plus U calculation on this system, basically just applying a U value to the chromium, that's what we do most typically. We change a lot in this band structure, but basically we don't get a band gap. Basically because of the type of problem I was mentioning this morning, the two of the states, because of the symmetry of this system, remaining degenerate to each other, and so they keep being half-filled or approximately so, and so they stick to a very narrow region around the Fermi level, so that they both are partially occupied. We will see this in a moment. Yeah, exactly. How is this realized in the output? So this is the output of our calculations. And you see these are the occupation matrices for the atom 1, which is a chromium, and it is for an atom that has a positive magnetization. So we'll have spin 1 mostly occupied by 3 plus half and a half, basically, or slightly more electrons, so 4 electrons, and almost completely empty states for the opposite spin channel. Okay, and now these degenerate bands are exactly related to these two states. Okay, having been degenerate, as you can see from the fact that they have the same occupancy, and since they are degenerate and fractionally occupied, they stick to the region around the Fermi level. So can we maybe play the same trick that Iurii was showing this morning to get an insulating state for the iron monoxide? How could we play that trick? So we need to find place for 4 electrons, right? So since we have these splittings between chromium D states, we have a group of 2 here, and then a single state. So why don't we impose that the occupation of these states be 0, and then we suggest the code that the occupation of these other 2 states become 1. These are already 1, so occupied fully, and we can check whether the code likes that, and a minimum can be found with a fully occupied state separated in energy from the unoccupied one. So that's would be the easiest way to find an insulating ground state. So in order to do that, we just need to play to do basically the same that Iurii was doing this morning, suggest the code through the starting NS eigenvalue, the occupation of these states, and then run the calculation, and we should obtain that the occupation matrix change this way. So the system actually likes our suggestion. So if we suggest to unoccupy the single state, it remains unoccupied, almost exactly so, and the other 4 get all occupied by 1 electron each. So we create we create place for all the 4 electrons in this channel of this material. And correspondingly, we are able to open a gap. However, this result depends on the value of U. For the U I've used in this case, we get that the total energy of this system with a gap, the way we just created, has a higher energy than the system without a gap. So it's opposite actually compared to iron oxide. And of course, we cannot in principle conclude anything from this in cases like this, just because there might exist. First of all, it can be the effect of all not so well converged parameters that we are using in this calculation that are that have been chosen with the aim of running fast, because we need to have them running in a reasonable time to show them in this tutorial. But it could also be a real case. So suppose that you have converged all these parameters very well, and you might be finding something like this. Then it might mean that there is some other way to open the gap. There is some other ways to break the symmetry and localize electron on the d states of this material. Okay, so let's try to do this in practice. So we go back to the to the tutorial. So we are inside day 2, and this is exercise 3 folder. So we can start from running the calculation with the input file as it is. So this is the input file okay, for chromium oxide, just similar to what you got for iron oxide this morning, and also cobalt oxide. And we add this Hubbard card here with almost 0 Hubbard U, just to have the code print the occupation number, because we want to see how they look like. So if we do this, basically code starts. You see the occupations are printed, even though we're doing a calculation basically with 0 U. And it will take a minute maybe to run through self-consistency.
Matteo, while waiting,
Yes.
There are 2 questions in the Slack.
Okay. Can you?
Yeah, if you want, I can read them.
Yeah, because I don't know.
So the first one, how do we realize that the third eigenvalue is good? Do we need to play all first?
No, the way I picked it is because of symmetry, in the sense because of degeneracy. Okay, so if you need to have one hole in the manifold of 5D states, you choose to place it in the state that's single. If you place one hole or one electron in a doublet state, the 2 states composing this doublet will be half occupied or half empty. So you don't solve the problem. So if you want to see an insulating ground state coming out from this band structure calculation, you need to have occupied states separated from unoccupied one. Okay, so the number of occupied states and the number of electrons should be compatible.
Thank you. There is another related question. I think it's on your screen.
Yeah.
Can we make any chemical assumption, that is to say, choose to occupy a particular DM orbital?
Yes. So we will see something more about this later, I think. Well, I think this pertains to the problem of breaking symmetry in some way, which I won't do this time. I won't do it in this hands-on because there is not enough time. I mean, to break the symmetry, sometimes you just need to break spin symmetry, and that's okay if you have already an antiferromagnetic compound. Other times it required, like for iron oxide I was mentioning this morning, you need to construct a supercell, then it's more complicated, and of course the cost of your calculation increases. So typically when you run with finite U, the system develops a wealth of local minima in the energy, which are different from one another. And then if you have a good method to push the system in different minima, then you can compare them. Okay, it's not always easy. I mean, the code doesn't always like the suggestion you can make through this starting an S eigenvalue in the code and so forth. So it takes a little bit of practicing to realize which state you are occupying, which state the system likes to be occupied, and so forth. Okay, so by now the calculation is finished. Let me just open the output. So here are the final summary. okay, with all the contributions to energy. And we got total magnetization 0 with absolute magnetization different from 0, which confirms the antiferromagnetic ground state. And then if we go look into the last iteration, it will print out the final occupation matrix. So this was obtained with with plain PBSOL actually. So we got three fully occupied states as before, 2 partially occupied ones, and then you get some more fraction of an electron also in the downspin channel, okay, because this is a more metallic ground state. Now, when we don't run the band structure of this, you can do as an exercise, okay? This will give us something. What is it? The band structure. This one, okay? So we're still here now. Okay, so you will run this band structure calculation as an exercise and see if you can confirm this. Now, if you want to get an insulating ground state, no, first let's run a blind plus U calculation, okay? Let me show this first. So for simplicity, I will use a U of 6. It doesn't really matter. I mean, the value reported here on the slide, I computed 7.86, but for the purpose of showing these qualitative things, it doesn't really matter what kind of value we put in. We want to understand how it works. Then later on, we'll do an exercise on how to get these values self-consistent. So here we put U equal to 6, and then we try to run same as before. We of course overwrite everything. Okay. There are questions. Okay, so we can give a look at what has happened here. This is now the FT plus U calculation with blind one. So where we just put a finite value of U on the chromium atom. Now we go look to the occupation. So you see it's not numerically the same, but very similar to what we got, to what I showed you before on the slide. So we get 3 fully occupied states down here, and 2 partially occupied one that will give this sort of metallic state with 2 bands almost degenerate to each other, sitting at very close to the Fermi level. Okay, so we want to play that trick of suggesting the starting occupation from input, and now we will do. In order to do that, let me stress something that Iurii said this morning. We need to go back and look how the occupation matrix looks like after the first iteration. Okay, so if we do this, we end up here. This is the first iteration. So before that, This is the initial guess the code provides for the occupation matrix. Then there is the first diagonalization of the Hamiltonian, and then it prints out the first guess for the occupation matrix. This is important because when we suggest the new eigenvalues for the occupation matrix, the code will change. We impose basically those occupation matrix at this level, at this moment. So after running the first iteration. So we'll take this occupation matrix and we'll change it accordingly to satisfy basically our requirement from input. So you see here the state that we would like to put empty is the third one. That's the important information we need. So it will be the first two that we would like to make them fully occupied, and the third one we want to suggest to be empty, okay? And of course, this is for spin 1 for atom 1, but also for spin 2 of atom 2. Here we go. There are the same atom, but with the opposite spin, so the same information for both. Now let's do that. So let me copy from the okay. So what does it mean? So basically we are suggesting that the third state, okay, of the first atom and with the spin 1, I never remember which is first, which is second of these indexes, be put to 0 after the first iteration of our self-consistent cycle. And then the first two states instead be attributed an occupation equal to 1. The same goes for the other chromium, the one with downspin, but of course for the down channel. So if chromium 1 has a majority spin, the other chromium in this antiferromagnetic ground state has the same thing, but on the opposite spin. Now let me show you what happens if I do this, but without a U. So what should we expect? Basically, what happens is, or what should happen is, that the code doesn't do anything different. So suggesting to change those occupations without the U doesn't change anything because the U is 0, so the termine energy that depends on the occupation has a 0 in front, and it should be doing, the code should be doing a normal GGA calculation. So it should go back to the usual PBS or ground state that we saw also at the beginning. I should have saved, of course, the first output, which I instead deleted, but we should be able to recognize it. So, so here is the occupation at the last iteration. As you see, if you remember, we got these three states fully occupied and the first two half occupied with some electrons on the downspin channel. Okay, precisely the same result that we got with PBSOL calculation at the beginning. So nothing really changes. If you want to change this state of things, so you need a finite U, of course, that encourages the system to take the occupation the way you want. So now we run with finite U. Say always 6. Now we should get something different. While we wait, so let me comment a little bit what's going on in the output. This is, of course, the same file that's been constructed. And this is the first iteration, the one I mentioned was important. So you still see here the usual guess that the code makes. This one, if you leave it as is, will give you the state that you don't like. So let's see how the code takes our suggestion from input. So this is still atom 1, right? Atom 2, initial occupation matrices. And then the number, and then the code says, I'm modifying the starting NS matrices according to the suggestion we provided in input, with the input value, starting NS eigenvalue. You see here, let's compare these matrices. This one, now things have changed, right? So the first eigenvalue is 0. It always order them in a growing order, okay, of eigenvalue. But I want you to realize how different this matrix is, or how similar to the previous one. Okay. So this is the new occupations, and below we get the old ones. So we can recognize now the states based on their components on the D state. So you see what we suggested to be unoccupied is 1 over square root of 3, 1 over square root of 3, 1 over square root of 3 of the second, third, and fifth D states. And we find this state here. It used to be the third one, right? In fact, we placed we suggested the code to modify the occupation of the third state, this one, and to put it to 0. And there you go. Then we suggested the first two to be updated to 1. So if we look now at these components, we don't exactly recognize this. Why is this so? Because the diagonalization routine, when you get basically degenerate eigenvalues, they give you two eigenvectors with a random phase. Okay, so there's no way to avoid that because you know, any linear combination of these two states would still be an eigenvectors with the same eigenvalues. But basically, you can recognize these other two guys here. Okay, it's almost the same. This vector is this one, so this vector is almost exactly as this one. So the other two having occupation of 1 consistently with our suggestion in input can be, but the remaining two. Okay. So let's go. Okay, now this has been modified since I opened it. And now we can give a look to what happened. So now we got an insulating ground state. And here it is. You see that the state we suggested to have zero occupation still has almost zero occupation. So the system liked it, liked this suggestion, got into this at least local minimum of the energy. And you see almost full occupation of the other four state, okay, with almost zero electrons on the downspin state for this first chromium, and of course the opposite happens for the other chromium that has opposite spin of opposite sign. Okay, so everything is good. Now we can run the NSCF. Bands. So we start this non-self-consistent calculation on the point of the path we've chosen for plotting the band structure. That should be the ones that I showed you in the slides. So it will take a while. Let me see if there are other questions. About the order of eigenvalues, okay, there are answers, but I also mentioned this morning. Okay, seems that there are not unanswered questions for the moment. Or did I do the same mistake as this morning? Maybe cell parameters are still like slightly different. I shouldn't have them different. Name? No, they look the same. Okay.
So there is one question about cell parameters.
Yeah. Yeah, I just checked them. So between SCF and bands, they look the same. Maybe it was referring to something else.
Yeah, it's about 1/2, 1/2, 1. So it's like y there is some deviation from the theoretically correct value.
Okay, so let me comment on this. So you see here these three vectors in terms of the cell dimension 1, which for this lattice is this one, this length, have coordinates like 1, 1/2, 1/2, 1/2, 1/2, 1, and 1/2, 1, 1/2. Okay, so these three vectors would describe a perfectly cubic structure. Now, if you relax these materials, they tend to deform, so to get away from the cubic symmetry, from the cubic structure, and these fractions are not anymore exactly equal to 1/2 or 1. So they become, typically they elongate along the 1, 1, 1 or compress along the 1, 1, 1 diagonal, which is the one joining this chromium with this chromium here. And so these coordinates change a little bit depending on the amount of deformation that the system wants to go through. Now we picked these unit cell with a deviation from 1/2 and 1 just to lower the symmetry enough in order to play these tricks. Otherwise, if you get, as I was saying this morning, if you get too much symmetry, then you get too much degeneracy, and you cannot you cannot play these tricks of choosing the occupation, etc. So the bands calculation is run. So if we go to see the README, you can try, will it work? You can try this now to run the bands calculation so we can get some picture, some figure. It's done. Yeah. And by doing this, I mean, this plot band is typically an interactive code, but you can also run it like this if you prepare a small a small input. Now this should have created some PS file of the bands. Yeah, and so we got so you see we got the separation of this 0 is always the Fermi level. And now we get a gap around it, separating occupied states down below from unoccupied ones. So the states that used to be degenerated and tangled around the Fermi level are now disentangled and separated from one another. So we got what we expected. Again, maybe this is not the only way to break the symmetry to get an insulating state, provided that this material wants to have an insulating state. Maybe you get away to another or in some other way, or you get to some lower energy ground state with a gap in some other way. I mean, breaking the symmetry some other way. This is just an example, and maybe you can try, but let me stress once more that if you have if these are the occupations, so you see exact degeneracy between these two and exact degeneracy between these two. Typically, these exact degeneracies are the result of symmetry. So if you want to break them, you suppose, for some reason, you believe that you should occupy these two, and then one of these, and then this one, and leave this one empty instead, then you have to break the symmetry that makes these two degenerate, okay? So this might not be that easy. Okay. Let's go on with the presentation now, because I'm done with exercise 3. This we have seen already. Okay, so what about DFT plus U plus V calculations now? And to explore these, we use silicon, okay? As was mentioning this morning, the band structure of silicon looks already kind of good with PBE or PBSOL that we've used here, although the energy band gap is underestimated from the experimental one, and other properties are predicted okay, not bad, but can be improved. And typically this kind of problem is approached with hybrid or self-interaction corrections to the DFT. We want to see if we can do a little better than that with U plus V. So, so we have here the typical input file for the bulk calculation of silicon, which has this FCC structure with 2 atoms in the unit cell, one sitting at the origin and the other one at 1/4, 1/4, 1/4, and this is the second silicon here. And again, the PBA plus U calculation that whose input is shown here features a 1.42 value for the Hubbard U, which is probably something that I have computed in the past. But again, doesn't matter in order to make this exercise. The important thing I want you to focus on is the different syntax. Okay, we have now for inserting the Hubbard V. So I'm making this part now bigger. So when you have a Hubbard, want to enter Hubbard V calculation, the Hubbard card for DFT plus U plus V calculation, you still have the Hubbard card, and you still need to choose atomic or orthoatomic. And here, more importantly than before, I advise you to choose orthoatomic. You can try, or as an exercise, to use atomic with a number U and see what happens to the band structure later on. And now, basically, you have to insert a little more information in the card. So instead of U, you say you want to apply a V. And the first line is basically an on-site V, which is a U again. So you are applying a V between silicon 3p state and silicon 3p states, where the first silicon is number 1 in the list of your atoms, and second silicon is also number 1. So you're basically applying a V between the 3p states of number 1 and the 3p states of number 1, which is exactly a U. You have to do that because although it might seem stupid doing it this way, because when you use V, you cannot input a line with starting with U. So you have to do this. And this is, again, the value of the U you want to use on silicon 3+ state, again, in electron volts. The second line is the new thing. So you're telling the code that you want to use a V between silicon 3p state, silicon number 1 3p state, oops, and silicon number 2 here in your list, which is the nearest neighbor of the previous one, also 3p states. And the value of this V is 0.25. Okay. So this is basically the simplest case to enter an intersite V between this atom basically and this atom. Okay. One may think, okay, but these are not this atom is not the only one being the first nearest neighbor of this one. Should I have all the 4 of them indicated in this list? No. Okay, the code only needs one of them, and then recognize which are the other neighbors sitting at the same distance from the first one, and put automatically the same V between all of them. Okay, so if you have I don't know, transition metal atom sitting at the center of oxygen octahedron, you need to put the V between the central transition metal and one of the oxygen, provided they are the same distance from the center. Okay, and the code automatically will use the same V for all the 6 bonds, let's say, between the transition metal and the oxygen, nearest neighbor oxygen. Then you can put also a second nearest neighbor V. That's not forbidden, of course. Here you would do, but here it's more complicated, and we'll come to this a little bit later, because the second nearest neighbor is not in the same unit cell anymore. So you need to know what this number would be for the second nearest neighbor, and I will tell you a little bit later. So here is the input file, exactly the same as before, but except for this change in the Hubbard card. Okay. So you can do still the same, you can use still the same procedure as before for running bands, okay, of silicon. So you do an SCF calculation, then a band calculation, non-SCF calculation for the key points along this path that we have used, and then you can extract some band file from the post-processing of these calculations. So this is the series of commands you have to use. Now we will do it, and these are a comparison between the band gap. Okay, so you can hardly see the differences, but if you have good eyes, you will see that this band gap obtained with only U is a little bit smaller than this. So if the band gap evolves in the wrong direction, okay, just because of the reason I was mentioning this morning, that the only U calculation, the U only calculation basically tries to impose a non-site localization of electrons by suppressing, among other things, the intersite, the hybridization of the states with its neighbors, while the V instead reestablishes that, so favors the hybridization with neighbors, and the gap, which in this kind of material is based on the splitting between bonding and anti-bonding states, basically gets increased. Now, in order to have quantitatively predictive calculation, you need, as I mentioned this morning, you need to have the V on site. You have to allow for basically the sp3 hybridization of S and P states on each of the silicon atoms, and also to have the V between P and P, P and S and P, and S and S. So it's more complicated than that, but we won't do this this afternoon. So this is what I was just mentioning. In order to get more reliable results, you need to do something like this. And you see here I have, see, for all these 4 couple, I have 1, 1 here, meaning that I'm putting a V between states of the same silicon atom, the first one. And automatically the code will treat the same the second one, because they are of the same kind. And then this means that I'm putting the V between the 3p states of the first atom, 3p and 3s, 3s and 3s, and 3s and 3p. Okay. Why do I need to specify 3p and 3s and 3s and 3p? Because if you think of it, when you have intersite type of these things, they're not bound to be the same. So if I had a transition metal and an oxygen, would be 3D, for example, and 2p, the reverse will be between, 3D and 2S, the reverse would be 2P and 4S. So the two channels are not the same and shouldn't be given the same value of P. Okay. So the band structure, it looks very much the same as before, but believe me, the gap increases and all other properties evolve in the right direction that we like. Same thing for the gallium arsenide, which we won't deal with in this tutorial because there is no time. Here, things are a little bit more articulated because the two atoms in the zinc blende structure are not of the same kind. One is gallium, the other one is arsenide, of course. And so you have to enter a V, on-site V, which is a U again, for the gallium 4p states, which is the first one, a V for on-site V between the 4p states of arsenium atom, which has these 2, the second one in the list here of atoms, so I have to put 2 and 2 here. These values I've chosen by chance, I mean, without computing them, and these are generic values. And then if you want to have an intersite V between just 4p states, you put V, gallium 4p, arsenium 4p, and you have to tell the code the numbers of these two atoms in the list of atoms, okay? In this case 1 and 2 because they're nearest neighbor. And I've picked a 1.5 electron volt value for the V in this case. So you can run this as an exercise and see what happens again compared to the band structure that you get from plain PB calculations. Okay, so let's see this in practice. Oh, was in exercise? No. Okay, so yes, we are in the right place. Okay, so the input file is already set up for a DFT plus U plus V calculation. And you can see that here, okay? We can run directly this calculation. It will be very, very fast. Run the SCF. You actually check. There is agreement between SCF and non-SCF in terms of Hubbard. I picked two generic values for U and V just to make things a little more clear. In particular, I've picked a bigger value of V. What is it called? Of course, didn't make through. It will run faster than the previous one.
Now there is one interesting question.
Yeah.
Shall I read it?
Yeah.
Okay, so what is the physical justification of on-site U in silicon? Is it possible to use DFT plus V without the Hubbard U, where the on-site interaction are treated at the DFT level, just to see if the gap is in grosso modo due to the inter-site interaction?
Technically, it should be possible. I mean, the code should not crash. Physically, I mean, the way I see this is the following. Basically, since we have had this nice introduction to Barnier function yesterday, we can say that physically it would make sense if you want to basically fix or tune a little bit the localization of electrons on in covalent semiconductors like silicon, gallium arsenide, germanium, carbon. Physically, what one should do is to do a DFT plus U on a Barnier function basis set, right? So the usual formulation of the DFT plus U, but instead of having atomic ground states, would make sense to have a Barnier function, no? So that would localize electrons, would help on electrons localize on bonds, okay, rather than on atoms. But now, suppose you have that. Suppose you have that that corrective term, that corrective Hubbard term that works on Barnier function, and to rewrite that on an atomic basis set. So you basically transform back each Barnier function onto the atomic basis set. You can always do that provided that the two bases are span the same Hilbert space, as we suppose. What do you get? You get on-site terms, sort of PP, PS, SP, and SS terms between sp3 kind of states for each carbon, and then you get also intersite term. You get more, actually. You get more complicated terms, but presumably these two are the dominant ones. So, I mean, having this plus V extension to the on-site Hubbard basically prevents you from having to choose a different basis set than atomic one. So gives more flexibility in this sense to localize electrons where the system wants the electron to localize, without having to choose a properly designed, let's say, a properly suited basis set to do that. I hope I answered the question. Let's check what happened. So we now do this one. We like. I didn't see it already created. Okay. There you go. So basically, in spite of the fact that you're using a U value of 1 electron volt, or actually 2 electron volts, and 1 electron volts of V, the band structure still looks pretty much the same as before. I mean, if you overlap them, of course, there would be differences, but qualitatively, it still looks the same. You can, as I mentioned before, you can try to see what happens now if you use atomic instead of orthoatomic. You will see a huge deformation of this band structure. The reason is that this material is covalent. So using atomic instead of orthoatomic means that you're counting twice electrons in the interstitials, because you're not orthogonalizing basically wave function, atomic wave function in the between atoms. Okay, so of course on the same atom the atomic wave function are orthogonalized because of their angular part, but between atoms there's no orthogonalization, there's no obvious orthogonalization. So if you don't orthogonalize them, they're not orthogonal, and it ends up what you end up doing is putting a V, sizable V on regions or on state that significantly double count electrons in the bonding region. And since this material has significant amount of charge density in the bonding region, then the error becomes significant as well. So better to pay attention when you use the V to orthogonalize the basis set. I mean, you can play with this kind of calculation, see what happens if you increase the V value or use that only in your calculation, and leave that as an exercise. Iurii, I guess we are. It's about time for you to pick up and do the next exercise, right?
Yep.
And then I'll go on with the last one. That's
okay.
Correct?
Yeah.
Okay.
Thank you, Matteo.
So let me stop sharing.
Okay. We are running slightly late, so I'll try to go fast. So we have 40 minutes. So let's say I take 20 minutes and Matteo takes the final 20 minutes. Okay, let me just go to the next exercise. Exercise 5, the calculation of Hubbard U. So far, we showed you how to use DFT plus U and DFT plus U plus V once you know the values of U and V. So far we assumed we know them. But now in this final part of the hands-on, we'll show you how to compute them using quantum espresso. The first exercise was about cobalt oxide. So let's do exercise 1 again for cobalt oxide and see how to compute Hubbard U. This is from my lecture of this morning, so I don't want to repeat it again. This is just a reminder about the self-consistency cycle, how we compute U and V, and we'll try to apply it now for cobalt oxide. So we know already the input file for cobalt oxide, so it's just a reminder from exercise 1. So we need to, again, first of all, perform a ground state calculation using PW code. Here, we already are familiar with the Hubbard card. So here we just initialize the U values to some small numbers just to initialize the Hubbard machinery, because later we want to compute the Hubbard parameters. So we need to inform the code somehow that we are doing DFT plus U calculation, even though the U is essentially vanishing. So once we perform the ground state calculation, the second step is the HP calculation, that is to say, using the HP code. If you're interested to learn more about this code, we invite you to check this paper that was published a few months ago. And at the top of this slide, we see the input file for the HP code. It's very simple, extremely simple, I would say. We have this prefix and output directory, which are exactly the same as in the input file for the PW calculation. Then the key input information is the size of the Q-point grid. You remember this morning I introduced the concept of the Q-point grids that is used instead of the supercells. So we have primitive cell with Q-point grid that is used instead of supercells. So here we have these keywords NQ1, NQ2, NQ3, which are all equal the same number, 2. So this means we use the Q grid 2 by 2 by 2. So in practice, we need to converge the value of the Hubbard U parameter with respect to the size of this Q-point grid, as well as with respect to the size of the K-point grid, which is in this case 3 by 3 by 3. And finally, the convergence threshold for the chi response matrix. It has some default value. I think it's 10 to the power minus 5, the default. Here we are using slightly tighter convergence parameter. So from our experience, we typically use 10 to the power minus 8 if it converges. If not, we increase it a little bit to 10 to the power minus 7. Here we use even larger just to make it faster. So the smaller the parameter, convergence threshold chi, the longer it takes. Okay, so yes, now we need to perform 2 calculations. The first, the ground state, and the second, the linear response calculation using the HP code. And this is the values that we should obtain. For the both types of cobalt, we should obtain the value of 6.7553 electron volts. So let's try to do that. Now we go to exercise 5. Okay. And here we have the README file. Let's just check that all is good in the input for the SCF with PW. Yes, all correct. So let's just execute it. So SCF calculation with the PW code takes less than 1 minute. But you will see that the linear response calculation using HP code is way, way more computationally expensive. We can roughly say it is 20 times more expensive. Of course, this factor of 20 is a bit rough because it depends on your system, on how many symmetries there are in your system, which Q-point grid you use, etc., etc. But it's really way more computationally expensive than the ground state calculation. You will see in a moment. And we don't have time to wait until when this calculation is finished. So now let's submit it. hp.x with the input from hp.in and write the output to hp.out. Okay, the calculation has started. You see here in the output, we see that the code will perturb only one cobalt atom. So atom which will be perturbed. In this case, it's only one cobalt. We have also second cobalt, but it's the code checked that they are equivalent. It checked the trace of the occupation matrices, and the code realized that they are the same. So they just differ by spin, and it in this case doesn't matter. So that's why the code perturbs only one cobalt atom. And for this perturbed cobalt atom, it reports the Q-point grid. So we have 4 by 4 by 4. Oh, excuse me. We have the Q-point grid 2 by 2 by 2. So in principle, without symmetry, we should have 8 Q-points. But since we have some symmetry, instead of 8 Q-points, we have only 4 Q-points. So factor of 2 smaller, which is great. We save a lot of computational time. And now the code will perform calculation for each Q-point sequentially, one by one. We need to do 4 of them. Now we're running the first one. You can see calculation for Q-point, which is actually gamma in this case. And you see the code performs iterative steps. After this Q-point is finished, it will do the second, then the third, and the fourth, and then does some post-processing and outputs you the final value of the U parameter. So these Q-point calculations are independent, so you can parallelize the calculation over Q-points. This is not done automatically, but you can do it by hand. Check the paper that I showed you before, this one, it's explained how to parallelize the calculation over Q points. So we can run 4 Q points simultaneously, and we can say Q1 time. Okay, we need to wait, as you can see, even for the first Q point, we already performed 11 iterations, and we need still to wait some time. Maybe it can take 5 minutes, maybe more, I don't remember. But that's the number that you should obtain, 6.75. And this is the so-called one-shot calculation of Hubbard U. Okay, now if we go back to our diagram, so this workflow, we performed ground state and linear response calculations. Next step is to perform structural optimization using the computed Hubbard U parameter. So here I show you the input file for the VC relax calculation, variable cell relaxation calculation. You can have a look at this input. For example, we need to specify the convergence threshold for the total energy and forces during this variable cell optimization. So cutoffs for the wave functions and for the density and potential, ECAT WFC and ECAT rho, are typically higher than in the case of the linear response calculation of U. You see here I used 35 and 280, while here I use higher cutoffs, 50 and 400. So this is so because forces and stresses converge slowly with respect to the cutoff, and also with respect to the K-point mesh. So here we use 666, and in the previous input it was 3 by 3 by 3. So from our experience, VC relax requires higher cutoff and denser K-point meshes. Then we need to specify ions and cell name lists. Here we use the BFGS algorithm for the structural optimization that moves ions and computes forces and stresses. And then at the end, we specify the Hubbard card with the value of the Hubbard U that we computed in the previous step, which is 6.7553. So we need to submit this calculation and wait until the code optimizes the structure at the DFT plus U level. Okay, let's check where we are now with the HP calculation. Okay, the first Q point has finished. Now the code performs the calculation for the second Q point. You see Q point number 2, and it reached already iteration number 4. It goes slower because for this Q point we have fewer symmetries, so that's why the code takes more time to converge it. So yes, it takes time, which we don't have now. But once the HP calculation is finished, we can perform the VC relax calculation. Let me just show you how to do it. So we need to open the README file.
Iurii, whenever you feel it's the right moment, we have a question in the chat.
Okay. So just I finished this part and I'm ready to answer. Yes, to compute the VC relax calculation, you execute this command. It's again the PW program, and you just execute it. Yes, please, Andrea.
Yes. So the question regards to the materials. Is it possible to truncate the Coulomb interactness in the Z direction by using assume isolated 2D in the self-consistent calculation previous to the HP calculation?
Yes, this should be possible. I never tried myself, but I think it is compatible. Yes. Now that I remember, we tried a long time ago, and we didn't really see any advantage of using that feature. So that's why we dropped it. So I don't remember by heart if it's all compatible in the code now. You can try and probably it should work. But as far as I remember, this was not really improving anything. Even without that feature, the Hubbard U was the same.
Okay, thanks a lot.
Thank you. Okay, so coming back to the VC relax, if you run the calculation, You can do it later on today after the hands-on as a homework. But you will see that the calculation should converge after 6 SCF cycles and 5 BFGS steps. This means the code performed 5 ionic moves and 6 electronic self-consistent calculations of the quantum equation. For each new geometry, when the code displaced atoms in some way, it performed a new SCF electronic structure optimization. And at the end of this run, you will see new optimized cell parameters and new atomic positions. So you can see atomic positions are still in high symmetry position. There is just some numerical noise because we use a bit too loose input parameters. But if you use tighter, you should reduce the noise. And cell parameters did change indeed quite a bit. So with this new geometry, we're arriving to this step of checking whether the input and output Hubbard U match within some accuracy and whether the geometry changed significantly or not. So our input value of U was essentially 0, while output is 6.76. And typical accuracy on the Hubbard U is 0.1 eV, which is very good for the majority of applications. So if we take the difference between 6.76 and 0, we get 2 big errors. So this means we need to go back in the cycle and do one more iteration and see where we come. So to do that, we come back to our input file. The story repeats. What we do here, we put our previously computed Hubbard U parameter, which is 6.7553. We put it here instead of 0. And for the cell parameters, we put the latest optimized parameters, cell parameters. All the rest stays the same. Atomic positions we don't change because it's essentially the same. There was some numerical noise, we can simply neglect that. But in general, also atomic positions must be updated. With this new input, we converge to the new ground state. But here, there is some technical aspect which is very important here. In the first calculation, which was DFT calculation, that was the metallic ground state. You remember we computed in exercise 1 the projected density of states, and we saw that it is metallic. But now we apply plus U, and we remember from exercise 1 that when we apply plus U, it opens a gap. So we went from the magnetic metal to magnetic insulator. But before going to the next HP calculation, we need to perform additional SCF calculation. This is so because if we don't do this additional calculation, but we straightly go to the HP calculation, the code will stop complaining that you are having a magnetic insulator, but you are treating it as magnetic metal because you use smearing. And this has some, then creates some numerical issues because there is some term implemented for metals, which is proportional to 1 divided by the density of states at the Fermi energy. And since you have insulator, you don't really have Fermi energy, you have a gap. You will see you have some vanishing density of states at the Fermi level. And when you divide 1 by a very small number, you get infinity, so singularity essentially. So we have magnetic insulator, but we treat it as a fake metal, and this will explode our calculation, HP calculation. So that's why we need to do the second SCF calculation, which allows us to go from magnetic metal to magnetic insulator. So there are a couple of differences. So on the left, we see we use smearing. On the right, we replaced it with occupations fixed. So it means it's insulator. Second, on the left, we have N spin 2, which is spin polarized calculation. We started magnetization. But on the right, we still do perform spin polarized calculation, but we don't use starting magnetization. Instead, we use total magnetization, which we know from the previous run. So after the first SCF calculation, you converge to the ground state which has zero total magnetization because it's antiferromagnet. So we just need to inspect the previous output and put here total magnetization 0. And finally, in the electrons name list, we need to put starting wave function and starting potential file. In this case, the code will not start from scratch, from linear combination of atomic orbitals, but it will really read from the temporary directory, which is output directory TMP. So the code will read the wave functions and the density, which were already well converged in the previous run. So we have very good starting point here because we don't start from unknown density or some very bad initial guess, but we really start from very good density and very good wave functions. The only thing that we do, we simply switch from the calculation of smearing to the calculation without smearing. That's the only thing. So that's a technicality which has to be used in magnetic insulators, ferromagnetic insulator, antiferromagnetic insulators. But we need to do this two-step procedure. And if we compare the output files of these two types of calculations, in the first one, which we treat as a metal, we have Fermi energy because it's metallic calculation. And total magnetization 0, it took 23 iterations to converge. Then in the second calculation, we remove smearing and we perform the insulator calculations. So now we don't have Fermi energy, but we have HOMO-LUMO, the highest top of the valence band and bottom of the conduction bands. And we see that indeed, HOMO is lower than LUMO. So indeed we have a gap. The total energy didn't change up to 8 digits, so no changes. Total magnetization still 0, as it should be. And we performed only 3 iterations to converge because we started from very good density and wave functions. So it's really sort of a refinement and refinement calculation, and when we switch from metal to insulator. And after these 2 steps, we repeat the HP calculation exactly the same as in the first run without any changes. And we obtain a new value of the Hubbard U parameter, 6.3695. And so on and so forth. And with this new Hubbard U parameter, we do a new optimization, DC relax. So that would be the end of the second iteration. And then we do the third iteration and the fourth. And then you can plot this kind of figure, where on the y-axis you have the value of the Hubbard U parameter for cobalt 3D states. And on the x-axis, we have iteration number. So we see first we computed U, which was 6.76. Then after VC relax and recalculation of ground state, it dropped down to 6.37, more or less. Then after the second iteration to third, the change is much smaller than from first to second. And finally, after third iteration, the first one doesn't change almost anything. So we really reach the self-consistency. So you see, it takes quite some number of calculations. It's not just one calculation. It really takes quite a bit of calculations. And yes, this is still our first run, but we're already at the last Q point number 4. And it's almost converged. Let's just wait when it finishes. But this is first iteration. Then you need to do 4 of them. So you need to multiply by a factor of 4. But that's the way it works. Doing it by hand is a bit boring. So during day 1, actually yesterday, you learned that there is a AIDA and there is a workflow implemented to do this automatically. So instead of doing it by hand, you simply can use AIDA with this so-called AIDA HP workflow, where you just press the button and an AIDA will take care of all these steps automatically. Okay, so maybe I can take, okay, let's check the output. Yeah, you take the file cobalt oxide Hubbard parameters, and we see that the first one-shot calculation of Hubbard U gives us the value 6.76. which is exactly the same value which is reported here. That was the first iteration. Then you can do later today on your own the second, third, and the fourth iteration. But first, don't forget to perform VC relax after this run. Okay, maybe 1-2 minutes to answer some questions, if there are any. I don't see any particular question that requires. No, there are quite a number actually. Is the HP calculation supported in the GPU accelerated version of the current version of QE? Yes, the answer is yes.
And there is also a question related to MPI parallelism that is somehow.
Okay, thanks. So yes, it can be run on GPU. I never tried myself. It was done by other quantum espresso developers. So you can run on NVIDIA GPU cards. It's implemented using OpenACC and probably some in CUDA. Okay, and for the MPI parallelization, I don't see it. If you can read it, please. Okay. Could we use MPI run for the HP code? Yes, absolutely. You can run MPI run, you use MPI run. The code uses the parallelization over plane waves. So yes, of course, you can use it. You can parallelize it over key points automatically, Q points bit by hand. You can parallelize it over perturbed atoms. And all this is described in the paper document in the HP code.
So there's a question that was signaled for discussion. Is the Hubbard correction compatible physically and numerically with the calculation of XPS and XF spectra?
Okay, thanks. Yes, we actually use the X spectra code of quantum espresso together with plus U and plus U plus V. And the agreement with experiments was not too bad. But we concluded that actually the global value of U was not good enough because it shifted the empty states too much. So we need more refined version of DFT plus U and DFT plus U plus V, because using the global value of U for empty states is not working very well. We have other projects related to this. So using the global U as a hammer to all empty states doesn't work very well. So yes, for those spectroscopies, we need to work more on these methods. They are not, let's say, as good as we would like them to be at this stage. Okay, I think I can stop here and let Matteo use the final 15 minutes before the end of the session with the last exercise with DFT plus U plus V.
Sorry, I forgot to activate my microphone. Okay, so I will resume presentation. Just 1 second. I just wanted to start from an aspect that I forgot to mention earlier on. About silicon, that is, I know actually. Okay, let me share. Okay. So what I wanted to stress is the initial part of the output of a U plus V calculation. In this case, it's still silicon. So this is the SISCF.out input file. Because if we run with a DFT plus U plus V calculation, At the beginning of the output, the code prints this part that is summarizing the values of u and v that it is using for running this calculation. So you see here the numbers, the indexes of the two atoms between which it puts either u or v, and then the distance between them in Bohr, and then the value of v. Okay, so I used the value of 2 electron volts as an on-site u for this last calculation, and you see that both the 1,1 term has a v of 2, and also the 2,2 term, because there are 2 silicon in the unit cell, and they're of course equivalent to one another, and so you get a value of v equal to 2 also for the on-site term of on the second silicon. Then you have, for each of them, you have 4 neighbors, right? Because you have tetrahedral coordination of these silicon atoms, and this is the distance for the unit cell I picked between nearest neighbor, always in Bohr. So you see that in the input I had a v of equal to 1 electron volts, and then I find it here. Okay, so this please check anytime you run a DFT plus U plus V calculation, check this part, because it will tell you if the code has seen the right number of neighbors or for each shell of neighbors, and whether it has put the right V you expect it to be using for that shell of neighbors. So if something goes wrong in this respect, you will realize immediately, and you don't waste your time going on with that calculation. You see that the 4 atoms that are neighbors of the first one are number 2, number 12, number 24, and number 28. Where does the code get these numbers from? Well, basically to have the neighbors that fall in neighbor cell, it constructs as far as I remember 3 by 3 by 3 supercell are centered around the one that you're using, and number somehow the atoms in those cells in this big supercell, and those numbers are taken from there. Okay, so are the index of the atoms in that big supercell centered on the one that you're using or giving it as an input. Same thing for the second silicon. Of course, since the second silicon is equivalent to the first, it should also have 4 neighbors, 4 nearest neighbors. In fact, it has 2, 1, which is the inverse of this one, and then 229, 233, 245. Okay, all at the same distances. So it worked. Okay, this being said, let's go to exercise 6, the last one of the day for this tutorial, and also run down the presentation. So the last example for today's hands-on is focused on this material, manganese oxide with sort of hexagonal crystal structure, okay, which is given in this plot on the right. So this is the corresponding input. You see the cell parameters here, those are highlighted in color here. So we have a triangular lattice on each plane, of which the manganese occupy all the vertices. And then we have the oxygen in this interstitial state, states with AB. So if this is A, this BC kind of stacking. I'm not sure this is a real phase for this material. I just got from the web and found it convenient to use because it ran relatively fast. So, and it will teach us how to enter the number of neighbors, which is an important information to give if we want to run, as we want to run DFT plus U plus V calculation for this structure. So suppose we don't know anything about this and we want to run this type of calculation. So we set up an input file like this, and then we want to check the band structure. So we do as before, we use xcrisden to find some reciprocal space path of k points where along which to run a band structure, or we use materials cloud as well as a nice feature. It's a nice way to determine a high symmetry path for band structure. And we run as before. And if we do that with PV, we get the usual metal because manganese has, in any case, partially filled these states. Okay, so low line here you get the energetics, the energy bands of oxygen. These are the p states of oxygen mostly, and up here you get the d states of manganese. Now, how to run an Hubbard DFT plus U plus V calculation? We need to add this Hubbard card at the end, and so we do it now. So I already input that here. Now the problem is that I might not know what is this number, what are these numbers. So suppose I want to enter the V between manganese and its nearest neighbor oxygen atoms, but I don't know this number for that. Here I know, I mean, this is an important guess, but I might not know what this number is. So what we do then, we can for example start from indicated generic guess like this, suppose. Suppose I do something like this. I try to fix values that supposedly don't give me any trouble of convergence for the U and V's. And now we run this calculation first. Did I do? Sure. Number 2 is not oxygen, so you see how it complains. I didn't do that on purpose. It's a real mistake. And now you get it running. So again, at the beginning, you should have written this summary. Now, since I didn't know what to do, you see, I put it 1,3 as a guess for the nearest neighbor. Turns out not to be the nearest neighbor. You see, here are the first 7 shell of neighbors, so including the trivial one, the on-site one, which is a distance 0. So the nearest neighbor would be a 3.68 Bohr distance from the manganese at the origin, while I have here 6.952, which is this one here. So I didn't get the nearest neighbor. Still, I don't know what is the index of the nearest neighbor. So what do I do? An easy thing that I can do is to use the HP code to get that information. So So this is a simple input file for the HP code, as the one Iurii was showing to you before. The HP, if you started from a previous SCF calculation done with the DFT plus U plus V, will automatically perturb also neighbors atom in order to give you the V also between atoms. Okay, so that is no problem. What I do here, I put this flag, determine number paired only equal to true. And what I will get, so it stops very quickly. And if I open now the file Hubbard atom, you see it will print for me these numbers, okay? For in an order, basically for increasing distance from the reference manganese atom that I put in the origin. It does that for every atom actually. So also for the second manganese and the third atom, that's oxygen, etc. So you see the first manganese has 6 oxygen neighbors. First neighbor, nearest neighbor 1, 2, 3, 4, 5, and 6, all at the same distance because of the symmetry of this crystal. And I know now that these neighbor oxygen are labeled by this number. So 48, 24, 12, 43, 19, 55. These are the numbers I have to pick. If I put 1, 2, would be the V between the two manganeses in the unit cell. Okay, I'm still doing an antiferromagnetic calculation, so I still need 2 manganese in the unit cell. And if I want to put a V between them, I can, in principle, provide that there is some finite value for that. So now suppose we want to compute the V, or run band structure calculation, we have to use this information. So let's keep that open. And so we can give a look while we construct the input file. So, okay, now we know 1, 3 is not the right choice. I want to put 112. And now, since the second manganese is of a different kind, I also have to indicate a V between this manganese and one of its oxygen neighbor. So I copy this line, I do manganese 2, that would be 2. And then I go here and pick a number for the second manganese. So let's say 2, 3. 3 is good. So it will be this. And then suppose I want also a B between the 2 manganese in the unit cell. That would be between 1 and 2. So this 2 is good. Okay. I'm putting just generic values here, okay? So we can run this calculation and then everything will work the same way as before. So if we do this calculation, I was using these other values. Here the syntax of this, what we just looked at, these are the values for the on-site manganese 3D states. This is for the oxygen 2p states, which usually we don't use. And then intersite between oxygen, between manganese and neighbor oxygen, nearest neighbor oxygen, and then between manganese and manganese, that would be next nearest neighbor. Okay. And I just show how to determine these numbers here. So we can go on. This is already we've seen something like that. Okay, so we're here, and we have these. We can run now these calculations. I'm afraid that something missing. Oh, here the slides are suggesting to use a very small value for the U and Vs. Now, of course, that's possible to do, but if you do that, the coder will probably run this as a metallic system, and it will take longer to run the HP calculation. So if you already know that it's an insulator and you can get an insulating ground state with some initial guess of the Hubbard parameters, then maybe it's convenient. You plan to compute U and V self-consistently, then maybe it's a better idea to use an initial guess that already give you some insulating ground state, so that the HP code, which you will use to determine U and V self-consistently, will run faster and take less of your time. So that's what I will do now.
Okay, Matteo, in principle, the coffee break was meant to start a couple of minutes ago. I think that it is worth to keep going, just for you to keep an eye on the timing.
Yeah, I know. It won't take long. I mean, I will just run, I think, or maybe I can just show what happens through the slides and then leave the test as an exercise to people who want to run these from the input files.
Maybe
no, I just want to say one more thing that I've discovered is missing from the directory here. So maybe let me run one more thing and then we'll stop. Iurii, you were saying something?
Sorry, just wanted to say yes, maybe just discussing the slides would be good to conclude.
Yeah, let me launch this and then I will discuss.
Thanks.
Of course, it didn't work. So now it's doing the SCF calculation, and what is missing from this directory is there's a second SCF file that Iurii was talking about, the one running the same calculation but as an insulator for the HP not to complain. Okay. So after this SCF calculation, you have to run another SCF with occupation fixed, and then NB and D equal to the value that we had before, and then total magnetization given to us in the previous, we have it here, 7.6 total magnetization. This would be with occupation fixed, and you have to start from file both potential and wave function for that to run faster. And I think that's it. And you use the same K-point grid, okay? So it should, of course, also the same values for U and V. So these ones now. Okay, I don't have. Wait, let me check. I got this value wrong. Yeah, not sure what is going on, what I'm doing wrong, because the file that I originally put in here got erased, and I don't know what to do. Let me show you what happens in the slides. So, well, this is what to be done. You see here, once you run the SCF calculation, you're supposed to extract a number of states from the first SCF, and then total magnetization well from the first SCF, use it in a fixed occupation calculation after that. So NB and D should be given in the number of states equal to the number of states, and total magnetization should be fixed at the same value as the first SCF calculation. So you're sure that the second fixed occupation calculation that you do has the same, reproduce the same ground state as the first one. So you also start from a potential and wave function. And then you run this and also HP on top of it. And hopefully it gets through without any problem. And so you, from the file MNO and manganese oxide Hubbard parameters, you get something like this now. So you get, again, couples of atoms, the distance here, and the corresponding values for V or U, if that's on site, in the last column. So you see, again, 6 neighbors all having the same V, and the same thing for the second manganese, that is the same as the first, except for the reversing the spin. And then you get also the same thing for oxygen, because you need to perturb oxygen now, because you want the V between manganese and oxygen, okay? So the code will perturb oxygen. And of course, the V between oxygen and manganese is the same as between manganese and oxygen. That's a nice check of consistency. We don't typically use these values here, the on-site U on oxygen, because they're too big, and in the self-consistent procedure, they typically diverge because of some issues with the linear response theory on for the calculation of U parameters on states or manifold that are fully occupied, like the ones on oxygens. So you can run a second step, a third step, as Iurii was showing, and then you, in 2 or 3 or 4 steps, you get converged values, so that are about 5.3 and 0.3 for the V, for the U and V respectively. So at this point, you can be happy of convergence and use these final results to produce a band structure. And you see, again, a gap appearing here. So the material is insulating as well. So that's it for this hands-on. So this is what concludes the hands-on, and we'll sorry for going over time, and we'll have a short coffee break, I guess, now, and then we'll reconvene, but on the other webinar, the lecture webinar, for the afternoon presentation now, right?